So today let's try to understand what is pigeonhole principle and how does it work and what's the way to prove this particular principle. So it's pretty much very easy to understand this principle. So let's take an example like let n be the number of pigeons, right? So you can just assume some number like 5 pigeons or 10 pigeons or something like that. Let n be the number of pigeons and m be the number of holes. You can say pigeonholes as well. So over here we have n pigeons and we have m holes. But the problem over here is the number of pigeon, we can say where the number of pigeon is greater than the number of holes. So if suppose we have 10 pigeons, then holes should be less than 10. It can be somewhere around 9, 8 or anything less than 10. So that's the condition. So you can just picturize it for your that will make the picture more clear. So in this particular condition, what will happen is at least one hole will contain more than one pigeon. So that's the basic principle is. So let me go through it once more. So let n be the number of pigeons and m be the number of holes. Where the number of pigeons is greater than number of holes, then at least one hole should contain more than one pigeon. So if I place like supposedly say 10 pigeons in say 8 holes, then when I go on counting the pigeons in each and every hole, I will be able to see that at least one hole will be there containing more than one pigeon. So let's try to prove this. The proof is very simple. So the condition or the approach that we will be using is the contradiction method. So what we will say is let's first have all this thing in place. Let's say let n be the number of pigeons and m be the number of holes, where we are just stating it as is, where n is greater than m. So let's try to prove that. What we need to prove, at least one hole should contain more than one pigeon. So let's take the method of contradiction as I said before. Let's try to write something which is irrelevant to this, which is contradicting to this. Then obviously we will arrive to a contradiction. Then we will say that whatever we have assumed is wrong. That means this particular statement should be true. So what we will be stating is, if possible, let each hole contain not more than one pigeon. So it's pretty much simple, right? So what we are saying is, if possible, let each hole contain not more than one pigeon. It is exactly opposite to this particular statement which says at least one hole should contain more than one pigeon. We are taking the exactly opposite statement over here. We are saying let each hole contain, that means each and every hole will have not more than one pigeon. So what does this mean? This basically means that every hole will contain max to max only one pigeon. So it can be 0 as well. We can say like the pigeonhole contains no pigeon also, then also it is fine. Or else it can have one pigeon as well, but not more than one. So let's see what happens by taking this assumption. So we will say let ni be the number of pigeons in ith hole, right? So let ni be the number of pigeons in ith hole. So what we are doing is we have m holes, right? So in every hole we are taking like ni. So let's try to picturize it so that it's more clear. So let's supposedly take so this is just for picturization, we don't have to write this in proof. So let's take, there are many holes with us, right? So how many holes do we have? We have m holes, right? This is first hole, this is second hole, third hole, and going on, this will be my mth hole. Fine. So every hole contains some of the other pigeons. We can say this contains n1. So as I said, like ith hole contain ni number of pigeons. So first hole will contain n1, second hole will contain n2, third hole will contain n3, and going on, my last hole will contain nm number of pigeons. So this number can be max to max 1, not more than 1. It can be 0 or 1 as well. So now let's try to sum up all the number of pigeons, right? So therefore total number of pigeons, what I can say about total number of pigeons, it will be sum of, as we all know, we have to just add all these numbers, right? Sum of ni, where I is from 1 to m. We are just summing up all the number of pigeons, n1 plus n2 plus n3 up till nm. So this will give me the total number of pigeons. So let me recall what was the total number of pigeons that I started with. N is the total number of pigeons. So I can simply say, right, so this is nothing else but my n which I am talking about, right? So let's try to proceed further. So I know one thing, like all these numbers are max to max 1. So what does this mean? So I can say that when I add all this, right, n1 plus n2 plus dot 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 like till nm. So since all the numbers are less than 1, I can say this particular value will be less than or equal to 1. Similarly, the other value, this will be less than or equal to 1. And going up to the last value, that is nm. So that will also be less than or equal to 1. So basically all this value will be max to max 1, right? As we assumed, like every hole will contain not more than 1 pigeon. That means the maximum number of pigeons will be 1. So for this value will be 1 or less than 1. This value will be 1 or less than 1, and going up to nm, this will be 1 or less than 1. So let's try to write it more clearly. What does this mean? This means we are just adding I from 1 to m. And let's try to picturize this. What does this value will be? So how many times we are adding 1 over here? So for this n1 we have 1, for this n2 we have 1, and going up to nm we have this 1. So basically this is m times, right? So you might have rightly assumed it. So these 1 I am repeating it m times. So for this one, and going up to nm. So since there are m holes, these 1 will be repeated m times. So 1 plus 1 plus 1 up to m times will give me like value as m, right? So if this is 10 times, this will be 10. If it is 11 times, 1 plus 1 plus 1, 11 times will give me 11. So similarly, since this is m times, it will give me value as n. But what this was actually, this was equals to n, the number of pigeons, right? So n is less than or equal to m. So if you see the point at which I arrived right now, this is contradicting something which we have assumed already. What we have assumed? We have assumed that the number of pigeons are greater than the number of holes, right? That was the basic assumption which we started with. But if you look at this particular point which we arrived right now, it is saying the number of pigeons is less than or equal to number of holes, which is exactly contradicting our assumption which we started with. So hypothesis which we started with. So we can basically say which contradicts the fact that what was our fact? Number of pigeon is greater than number of holes. So therefore, why does this contradiction occur? So that was because I was assuming something which was not true. So what was I assuming? I was assuming that let each hole contain not more than 1 pigeon. So this is not true. What does this mean? This is not true means each hole will, so we are saying like each hole will not contain more than 1 pigeon. So that means at least 1 hole should be there which contains more than 1 pigeon. So we can say therefore there is at least 1 hole, we can say therefore at least 1 hole should contain more than 1 pigeon. It's exactly true, right? Because we were assuming that no hole will contain more than 1 pigeon. That's arriving to a contradiction. So we can say that that's not actually true. It's not true that each hole will not contain more than 1 pigeon. This is not true. That means that opposite of this is true. So that means that at least 1 hole should be there which contains more than one pigeon. So that's the proof of pigeonhole principle. It seems it's very much easy to understand. Now let try to proceed to the other theorem or the other principle, which is an extended form of pigeonhole principle that is much easier than this. So let's see what is extended pigeonhole principle now. So let's start with extended pigeonhole principle. So the extended pigeonhole principle says that let n be the number of pigeon placed in m pigeonholes, then one hole should contain at least n minus 1 upon m plus 1 pigeons. So let's try to understand this statement first. So it's pretty much straightforward, right? So we are placing n pigeons in m pigeonholes. Now the thing to note over here is we are not saying like the number of pigeons should be greater than the number of pigeonholes. There is no such criteria over here. So we are just placing any number of pigeons in any number of pigeonholes. Then it says that one pigeonhole should contain at least these many number of pigeons. So let's try to prove this. So again we will be using the same method of contradiction. So let's start the proof right away. So we can say first we will just state everything. We will say let n be the number of pigeon, n be the number of pigeons, and m be the number of holes. Then here we don't have to say that number of pigeon is greater than number of hole or anything like that. Yeah, so before proceeding further with the proof, let me just clarify what does this mean. So this is basically floor function. So just to give a high level, what is floor function? So whenever I say like floor function, floor value of 3.14, so it will be basically 3. So just to picturize it, it's very much simple. So if I take this y-axis, so if I say some point over here, say 3 and 3.14, right, it will be somewhere over here 3.14. So when I say floor value of 3.14, so we are basically taking the value which is below this particular value, like the integer below this particular value, so that will be 3. To give an example, we can also say like if I say minus 2.34, I just need to find floor value of this particular number, minus 2.34. So where is minus 2.34? So it will be like if this is my 0, if this is my origin, so this will be somewhere over here, right, minus 2. So minus 2.34, it will be somewhere below this minus 2, somewhere over here. So when I say floor value of this particular function, again I need to take a integer which is below this value, so that will be obviously minus 3. So floor value of this will be minus 3. So as the name suggests, floor value means we just have to figure out the integer which is just below that given point. So sorry, so to be specific, when I say floor value of 4, so since 4 itself is an integer, so 4 itself is an integer, we don't have to go below for the other integer. We can just directly say, yeah, my floor value of 4 is 4 itself. If it was 4.1, something about 4, above 4, then floor value will be 4. So that's pretty much simple. So that's what floor value means. So we will be needing this concept when we do sums based on extended pigeonhole principle. So let's proceed further. So as I was saying, let n be the number of pigeons placed in m pigeonholes. Then I just need to prove, right? So I need to prove that one hole should contain at least these many number of pigeon. So as a contradiction, what we will be doing is we will be stating something which is exactly opposite to this. So it says one hole should contain, right? So opposite to this, we will say that all the holes will, all the m holes, right, all the m holes will contain at least, instead of at least we will use at most as a negation of this. So this says this function plus 1, right? So we will take something less than this. So we can simply say let if possible, we can say let if possible all the holes, we are just trying to make a negative statement of this particular thing which we need to prove, so that we can arrive to a contradiction. Let if possible all the holes contain, as I said, at most, I will say at most what, less than this, right, something less than this. So we can just ignore this one, so that will be more precise. So I can say at most these many pigeons. So we are taking exactly opposite statement to this what we need to prove. So my negation statement of this is all the holes, So for one hole, I am taking all the holes contain at most these many number of pigeons. I am taking one less than this. So let's see if I am arriving to a contradiction, then we are done with our proof. So let's try to proceed further. Let's try to picturize it first, as we did for the previous pigeonhole principle as well. So how many holes we have right now? The same, we have m holes, first hole, second hole, third hole, and this is my mth hole. Every hole is containing n one pigeon. So here also we will say that let ni be the number of pigeons in ith hole. So as we did for the pigeonhole principle, the same statement we will be using over here as well. Let ni be the number of pigeon in ith hole. So this means that first hole will contain n1 pigeon, second hole will contain n2 pigeon, third hole will contain n3 pigeon, and last hole will contain nm pigeons, right? So now I know that every number, all this number are like as I stated over here, all the hole contains at most these many pigeons. So all these numbers are max to max this particular value or less than this. So I can say, like when I add this thing, so I can say therefore n1 plus n2, when I go on adding all these values, right? So all this value will be less than or equal to, so since first value is max to max this particular thing, right? So I can say this is less than this, plus the second value, again the second values, the second number is all the whole contain at most these many pigeons. So this number should also be less than or equal to this. So again for this n2 I will use the same function again, and going up to the last value, for the last value as well I will have the same function which I will write, right? So as you might have rightly assumed, as we did in our pigeonhole principle, these are how many times we are doing it? We are doing it m times. So we can simply say, right, so this so I can say therefore I can write this in mathematically, we can write this simply as ni from 1 to m, just to reduce the space which you are consuming, less than or equal to, we are repeating this how many times? We are repeating this same term m times. So I can simply write this as n minus 1 upon m times m. We are adding this m times, so we can just say, instead of writing this every time, we can just say we are adding this m times, so this times m. So we can simply say that we can cancel these m's off, right? So what we are left out with is sum of ni I from 1 to m is less than or equal to n minus 1 with this floor function. Now let's try to picturize the value of this particular thing. So as I said before, when I say floor function of 4, it will be 4. Floor function of 5, it will be 5. Since these are already integers, the value will remain same. Yeah, if it would have been like 4.1, or like if it would have been 3.9, then I will have to figure out the integer which is below this 3.9, so that will be 2. But if it is a proper integer, then it will be exactly the same value which we are talking of. So similarly, if you see over here, n is a number, right? Number of pigeons which we are talking of. N minus 1 will be a proper number, like it will be a proper integer. So n minus 1, if it is a proper integer, the floor function will give me the same value as we saw over here. It will give me the same value, n minus 1. Now let's proceed further. So what is the sum of all this n, sum of all the pigeon? So what is the number of pigeons that we have with us? N is the number of pigeons, right? So when I add all these numbers, so I will be arriving to n. So it's basically adding up all the number of pigeons. So we have n pigeons, so obviously the answer will be n, and this is less than or equal to what we are arriving over here, it is n minus 1. So you can see it is clearly a contradiction, right? N is a number, so any number cannot be less than or equal to the number minus 1. So for an example, if I take 5, so here it will be 5 minus 1, that is 4. 5 cannot be less than or equal to 4. So it's pretty much a contradiction, or we can say which is an absurd, which is something against the rule of math. So we can say which is not true. So this is not true, obviously for any number it is not true. So we can say therefore our assumption is wrong. Our assumption is wrong. So what was our assumption basically which led to this contradiction? We were assuming that let if possible all the whole contain at most these many number of pigeons. So this is not true. That means that something opposite to this should be true. So opposite to this is nothing else but the statement which we were taking, right? So basically we made this statement over here which was negative to this. So this statement itself is not true. That means I can say my statement is true. So I can simply say that then one whole should contain at least this plus one. Just to be more clear, right? So when I say that this thing which I took over here is not true, so this is not true. What is not true? It's saying that all the holes will contain at most these many. So this is the maximum number of pigeon that can have. That is not true. That means it will have something more than this. Something more than this means we can just add a 1 to this. So I can say therefore one hole, there is one hole will contain n minus 1 upon m plus 1 pigeons. So that proves extended pigeonhole principle as well.